Good day, everybody. So let's take a look at what we have for our review today. So in this session, we'll focus on aldehydes and the ketones, broadly speaking. We'll take a look at their chemical reactions and some other properties and the trends in those properties, right? So, but first of all, let's take a look at the fundamental things, such as, for example, if we look at the aldehydes and ketones, what we are going to notice is that they have something in common, such as the carbonyl piece of the functional group, right? So here I'm just going to show some random aldehyde, so which is going to be looking like that, right? So this one contains like 5 carbons total. So it's going to be always a good idea to keep some kind of examples of like aldehyde molecule or alcohol molecule, right? In your mind, in your like set of knowledge, so to speak, as well as some examples of chemical reactions, right? So because if you keep those kind of fresh in your memory, so then it will be helpful when you encounter some sort of like reaction problems, right? Or if you encounter some questions like give me some example of like whatever aldehyde or ketone, right? And then how they can like interact with some other things as we evolve our knowledge, right? So if you take a look at the ketones, so it's going to be something like that, right? So it's going to be kind of like similar to aldehyde, but at the same time kind of like different, right? Significantly. So we'll have the carbonyl group, right? So but now if you notice, so this carbon will be capped with 2 carbons on the sides, right? As opposed to aldehyde, we have only 1 carbon cap, and then we have the hydrogen cap, right? So that's kind of like crucial difference between aldehydes and ketones, right? So both of them will have the carbonyl group, which is represented as this C double bond O part, right? So, and then oxygen obviously has 2 lone pairs here as well. So you just kind of like, as you draw them, right, you can have a practice, right? Just don't ask, but like draw those lone pairs, right? So that will be helpful, especially, yeah, if there's going to be some kind of question that will ask you about the lone pairs, okay, well, you'll be like all set, right? Because you have practiced this before. So another kind of like thing that we can consider here, so we'll have in these molecules in particular, right, a bunch of CH bonds, right, which are considered non-polar because of the 2 close electronegativity values between carbon and hydrogen atoms. However, it's not the case for when we consider carbon and oxygen in the carbonyl group, right? So there is a substantial difference in electronegativities between carbon and oxygen in the carbonyl group. So consequently, we are going to use so-called partial charges, right? Delta plus on the carbon because it kind of like partially loses electrons towards, like in those bonds, towards the more electronegative oxygen that attracts electrons towards itself and becomes, as a result, partially negative, right? So same here. So don't forget about that, right? So this will kind of like lead to future ramifications, such as now we're going to take a look at some properties, right, of those things, right? So let's take a look at the perhaps how they could interact, right? So here you are going to have the dipole moments, right? So if you just take a look at the interaction between, let's say, multiple molecules of this aldehyde, right? So we will have some sort of interaction happening between the molecules. We'll have a particular IMF, intermolecular force, which is in this case going to be dipole-dipole interaction, right? So those kind of like positive and negative ends will be meeting, right, in space. So meaning kind of delta minus on the oxygen will have to kind of like meet the delta plus of the carbonyl of like another aldehyde molecule, right? So, and then they will be able to like exercise this like physical interaction because as we know from physics, the negative and positive charges will attract, right? Opposite charges will attract. So don't try to attract like carbon delta plus with another carbon delta plus, they will repel, right? So like position your molecules accordingly if you were to show this like on paper, right? So it's going to be maybe something like, let's say, another aldehyde. So not necessarily this molecule, but maybe we have a mixture of aldehydes. Who knows, right? It's going to be something like this. So I'm going to put carbon here, oxygen a little bit farther, and then we'll have this delta plus on the carbon and delta minus interaction. That's your like dipole interaction, right? With the dotted line here. It's a little bit small, but you kind of like get the gist. It's about your positioning of the molecules on a piece of paper in the like sensible fashion. So then same with the ketones. Then if we add maybe some sort of other molecules such as H2O, then we are going to encounter the hydrogen bonding that will be present between the molecules of like water, right, which like can be found in lots of ketones, right? So as the like, compound in the lab. So sometimes they can be contaminated with the water, right? So then why does that happen, you might ask? Because there is the hydrogen bonding event, right? So we have the OH bonds with the hydrogen, right? Apparently in the molecule of water. And then we also have the charge distribution, right? Such as like delta minus, delta plus, and delta plus again. So turns out that we have delta minus on the like ketone molecule, for example, right? So then from the physics perspective, we can have this delta minus delta plus interaction. So this kind of hydrogen bonding tends to be quite strong, right? So if we remember the hierarchy of bonding, right, dispersion forces are very weak, right? Then the dipole-dipole interactions are a little bit stronger. So then finally, as we move to hydrogen bonding, that's going to be the strongest out of the three. So here we go. We have quite strong interaction, right? So due to that strong interaction existence, so if you, let's say, somehow like expose like ketones, right, that you have in some sort of like, let's say, beaker, for example, right, or whatever it might be, flask, right, to the like water, to the ambient environment, which inevitably will have like some moisture in it, right, in a lot of cases, then you will have this contamination of the ketone with the water molecules because they tend to form quite strong hydrogen bonding interaction, right? And the molecules of water cannot just like simply go ahead and leave, right? So the ketone molecules and keep it like uncontaminated, right? So that's just kind of some kind of broader implication, right? So why, for example, in a lot of cases in the lab environment, you can kind of like find the almost always water contamination in aldehydes and ketones, but it is just like something to think about on a like broader scale, right? Because inevitably we would like to connect those micro properties with macro properties. Speaking of which, we can take a look at the solubility, right? So this is something that we can see kind of like with our eyes as we, let's say, like put our compounds into the water as a solvent, for example, right? So if we take a look at the solubility, so comparatively, like what we can think about is that we might have some solubility present, right? So between the aldehydes or ketones and the water molecules, right? So then, but then again, it depends on the structure, right? So if we think about some kind of like very simple aldehydes, such as this one, right? So maybe it's going to be this compound, right? So this one does exist. So it is the formaldehyde, right? So this compound is very much like similar to water, right? If you think about the structure. So they both have like oxygen, right? So water molecule also has those kind of like two hydrogens, right? So there is a high chance that this compound will be quite miscible, right? So you we'll have to like make some estimations based on the structure, and a lot of times it's about the comparison, right? So of the structures. But if you have so they're likely to be miscible, right? But if you have a comparison, let's say between the water molecule and this aldehyde, yes, so it's still an aldehyde, right? But look at other parts, right? Let's say I'm going to kind of like draw a little bit more carbons here in the chain, right? So now it's going to be a huge number of carbons in the chain. So in this case, you are going to have a lot of alkane characters. So if we kind of like circle this alkyl chain, right, we can say that this is just comes from an alkane, right? So albeit this alkane like was functionalized with a functional group of aldehyde. So in this case, so this molecule looks a lot of like alkane, right? So there's not so much of the there is going to be the polar character in it, so but it's going to be a lot of atoms that constitute the non-polar bond, right? So, and then this molecule looks a lot like an alkane. Alkanes are not miscible with water. Consequently, we can speculate that this compound will be having lower miscibility than this lighter aldehyde in water, right? So it's very likely that this compound might not be miscible at all in water, right? So don't be kind of like 100% sure, so to speak, or definitive in your answers. You can use those words like might and may, right? So because you kind of like assess the situation, and you keep in mind that like we have the tenet that chemistry is an experimental science. So like we need to do the experiment, right, to be able to say, well, this is soluble, this is not soluble, and stuff like that, right? So that's when we can use those kind of definitive like what's it called, descriptions, right, to our conclusions. So then same is true about ketones, right? So for example, if you look at like acetone is a small molecule, right? So that's going to be this one, right? So it is going to be only containing three carbons, right? Not a lot of carbons, right? Compared with this ketone, for example, that has a lot more carbons, right? Maybe it also has like a phenyl ring on it all of a sudden. So in this case, you could say, well, so there's going to be lots of non-polar character in this ketone. So this ketone will be will be likely not soluble in water, or it will have like much lower solubility, much lower miscibility with the water compared with this ketone molecule, because it is much smaller molecule. So it has higher chances to be soluble, or at least it will have higher miscibility chance, right? So in water than this molecule. So maybe they will be both like poorly miscible, but if anything, if we compare their poor miscibilities, the miscibility of this huge ketone will be smaller, right? Will be even poorer than, let's say, the poor miscibility of smaller ketone, right? Because this ketone has much more non-polar character imparted to that by this like alkyl chain, right? Alkane kind of like root of the ketone, which is like here, and then alkanes are not miscible with water, right? So, but we can have some kind of like very small maybe miscibility. We can speculate because we have this polar group, which can interact via hydrogen bonding with the water molecules, right? That will supply the hydrogen for the hydrogen bonding. So yeah, lots of factors here to consider. So now let's take a look at like alcohols. I think we also were talking about alcohols to some extent, right? Building up towards aldehydes and ketones. So alcohols, as we recall, so that's just going to be good for our review purposes, must have the OH group attached to the carbon, right? So what do I mean by this? That's what I mean by that. So you need to find this. So that's what makes an alcohol, right? And then, yeah, you'll have carbon with its respective like H's in this particular example. So this is going to be our, let's say, like alkyl chain here that's kind of not involved into the alcoholic group, which is going to be like this one. That's our like alcoholic group. So what's so special about that? So as we like saw, so we can call this, for example, maybe this one will be 4 carbons here. Let's call it R, for example, right? And then we will highlight CH2 with OH specifically. So what's going to happen is that this alcohol will be more like water, right? Because if you put the water, HOH or H2O, you need to be able to write it in like various ways, right? So because it's for our chemical reactions perspective, we'll be very much interested in this kind of like OH bond breaking, right? For the case of like making various products, for example. And here, if you write it out like as such, right, you will see that there is going to be a lot of water character, right? So water has this like HOH, and then alcohol has like RCH2, for example, in this case, NOH, right? So they are very much similar to one another. So we'll have a higher generally solubility of alcohols in water compared with aldehydes or ketones, because aldehydes don't have the OH group, right? So they have the polar groups, but they don't look like OH in the water, right? So if you like remember what the aldehyde or ketone function groups look like. So that being said, alcohols have a higher chance of higher miscibility with the water, right? So, but at the same time, also need to pay attention to this like nature of the like R group, right? So alcohols could be like pretty short molecules, right? If we think about methanol, so this will look like this, right? So it is just very small as well, also has this OH group, right? And looks a lot like water, right? So except we are going to kind of like switch this H obviously to the methyl group, right? So if you look, they're also like close molecular weights, right? So things like that. But if you have if you have a look at some other alcohols, such as this guy, for example, let's imagine that we are going to have some kind of like huge alkyl chain here that comes from some sort of alkane, right? So then in this case, you are going to have less similarity between this alcohol and the water molecule, right? So because we have much different molecular weights, and then also uh, this has a lot more carbons, right? So than this alcohol. So this alcohol has a lot of, so to speak, alkane or alkyl character, and then we can speculate that it might be soluble in the water, but comparatively, compared with the methanol, right? So this alcohol will have much lower solubility, miscibility in the water. Maybe it will be completely insoluble, right? So there is a chance for that as well. So this solubility will be much higher for methanol than for this like huge alkyl chain alcohol. So yeah, that's again like something to keep in mind, right? So a lot of in a lot of cases we need to like be able to compare molecules, right? So like what do they have in similar? That's going to be the OH group, right? So what do they have like in common? That's OH group. What do they have not uncommon, right? That's going to be methyl versus this kind of like huge alkyl chain. So things like that. So you need to be able to like pay attention to details and then kind of like compare things, right? So then, okay, let's move on further a little bit to our like favorite hybridization questions, right? So if you look at the alcoholic molecule, so that's going to be, let's say, your example of an alcohol looking like that, right? So you have your, let's say these are some sort of like H's, let's say just methanol, right? So what's the hybridization here on this carbon? So this one is going to be sp3 hybridized, right? The geometry will be tetrahedral, which is peculiar to sp3 hybridized carbons. If we look at the molecule of some sort of like random aldehyde, so call it like R, let's imagine it is a hexyl, right? So whatever that is, so that's up to you to remember. And now all of a sudden it has hexyl, it is attached to this like aldehyde functional group. So this guy and this carbon specifically is what? It is sp2 hybridized and it is trigonal planar. So if you look at this, it looks like a triangle, right? And it is a planar as well. So same is true about hybridization of the sp2 hybridized carbon, sp2 carbon in the carbonyl chain, in the carbonyl group of the ketone. Let's say we have here methyl and maybe methyl again, right? So this guy, this carbon here in the ketone carbonyl group is also sp2 hybridized and it's also trigonal planar. So as you see, like you can draw it like several times and you will see kind of like this pattern, right? So single, single, double bond, single, single, double bond. So maybe you draw it like 10 times and then you'll kind of like have a better grasp of that. So yeah, just like something to like think about, right? So yeah, don't underestimate the power of like practice and drawing things by hand, right? So especially if you draw like various structures, right? So just kind of like trying to recall, okay, what's an aldehyde? Let's draw some examples of aldehydes with like 7 carbons, maybe with an aromatic group, right? So even like as you review, you can question yourself and then try to like generate those structures by hand on a piece of paper. So that could be like pretty good for your like factual knowledge kind of acquisition, right? So then what else can you do? So you can also pay attention to the ionization, right? So alcohols are ionized in terms of this OH bond. OH bond can break, right? And then what's going to happen is that we are going to have the acidic character to alcohols, right? So which means they will have to generate a proton, right? According to your general chemistry knowledge. So they will be dissociating like that. So obviously, so just kind of like right away show H plus, and you already have some kind of like partial credit, let's say, to your name, right? So that's pretty good. That's what kind of like every asset should do, right? So if you think about HCl, HF, maybe, I don't know, what else is there, like H2SO4, they all have in common what? So they can generate or put out the H plus on the product side, right? So that's like what we mean by showing the H plus on the right side of the reaction arrow, right? So alcohols also can do that because why? We have the polar OH bond. OH bond. It is polar. It can dissociate, right? Non-polar bonds such as like CH, they don't typically dissociate for our like in our conditions, right? So there are ways to dissociate CH bond, but it's like more advanced level of chemistry, right? So which is kind of getting like popularity only like now, like this decade, for example. So, but for now, so we know that CH bond, why is it not dissociating? Because the electron negativities are pretty close, right? It's even distribution of that electron density here between C and H, and neither of them wants to draw the electrons towards itself and break the bond that way, right? So, but alcohol can do this dissociation of the OH bond because oxygen, as we remember, is delta minus. This one is delta plus. So eventually, at some point, oxygen will be able to draw the entire pair of electrons towards itself, and then it will be able to make ions, right? So what do I mean by that? So that's what I mean by this. So we'll have our CH3, just leave it alone. It is intact, right? So then we'll have O and then H plus and H plus on the right side. So this one, let's just forget about this for now, right? So these are this is going to be our like right side of the reaction, like H plus will be generated. Okay, great. So now what's happening to this alcohol, right? So to the oxygen. So that's what we need to figure out. It's a little bit more difficult, but it's okay. So what you need to do is that look at this oxygen, right? And realize that right now, before dissociation, it is just a neutral atom, right? So with surrounding 1, 2, 3, 4, 5, 6 electrons in its like outer energy shell, right? So now what's going to happen is that let's say there are electrons which are colorized, right? So we will maybe make them, let's say, red on oxygen. That's the native oxygen electron, right? That was participating in the OH bond. And now we have also the blue electron of the H, right? So what happens after the bond breaks? So basically, turns out that it's not a homolytic cleavage, so to speak, right? It's not like oxygen gets its red electron and then hydrogen departs with its blue electron, right? So we do not make hydrogen atom here. Like we don't make H with a blue dot, which is a hydrogen atom. We make a proton, which is H with a plus, right? What happened here? So what happened is that the blue electron of the H was acquired by oxygen because it's more electronegative and it likes electron a lot more than hydrogen. So now, so you have the newly added electron, so which was shown by this curved arrow, newly added electron on the oxygen atom. So now, if you count the surroundings of the oxygen in terms of the electrons, so that's what you're going to get, right? So you used to have 1, 2, 3, 4, 5, 6. Now you have a lot more. 1, 2, 3, 4, 5, 6, and 7. You have the seventh electron. So you used to have the neutral charge in the oxygen. Now you make it gain an extra electron. Consequently, that's why you are going to have the negative charge as a result, right? So, and then that's going to be applied to any alcohol. And then any alcohol will, like, generally for now will tend to dissociate, right, and then make H plus, right? H plus will be the same, but the counter ion will be dependent on the alcohol structure. If you have here CH3, then CH3 will be saved, right? So if you have here a phenyl, then the phenyl will be here instead of CH3, right? So just redraw that part, don't touch it. So you will only be touching the OH bond upon dissociation of the alcohol. So yeah, just some segue to chemical reactions, right? And then now we're going to take a look at more chemical reactions of your, what's it called, aldehydes and ketones, right? So Here we go. So let's take a look at some examples. And here we'll encounter some kind of like new terms for this session, right? But hopefully they will not be new to the people who have been following the course material. All right, so let's take a look like next like reactions, right? So reactions. So one of them is the like addition, right? That's like broad terms. So, but more specifically, we're going to add hydrogen molecule or like HH, right? Two atoms of H, basically to our like aldehyde or ketone. And in more specific terms, it's going to be called reduction, because by reduction we mean from the organic chemistry perspective, generally the increase as a result of the reduction in the product in the number of hydrogen atoms, or we can also think about the decrease in the number of oxygen atoms, right? So one of those things will happen. So in terms of like aldehyde, let's say like some kind of like random aldehyde will be reduced, right? So here I'm going to show explicitly some things, right, for our learning purposes, plus H2. H2 is going to be the reagent here, right? And then PT will be part of the conditions. That's your catalyst, platinum, right? Catalyst, reagent, reagent. So then you will have your reaction arrow. And then here, let's say we go down, but it's going to be the right side, I would say, technically, of this reaction. So we're going to show the product, right? The product will be like that. So these two electrons will make the bonds. We'll make the OH bond and we'll make the CH bond, because carbon can provide an electron to make a CH bond and oxygen can donate an electron to make an OH bond, right? So because these bonds, so they will be donated because this bond will be broken. So the carbon-oxygen pi bond, some people are pointing out, will be broken. Sigma bond will stay put, so that's all good. So now we are going to redraw 1, 2, 3, 4. So that's our structure here. So for carbons, all good. So then leave this kind of like CH bond alone, right? So then you are going to leave the sigma bond, and now things are kind of hanging in balance, so to speak. So we have two H's, so they're coming in here and there, for example. Oxygen provides an electron, carbon provides an electron. Electron on H incoming, electron on H incoming. So then you will connect to make a covalent bond, right? So that's your Gen Chem knowledge, right? So what's a covalent bond? Please remember or know and be able to explain what it is, right? So, and now, as you see, you are going to get nothing more than an alcohol, right? What's the hybridization here? What's the hybridization here, right? So like try to ask yourself those questions, right? As you just look at that, as one of my instructors said, oftentimes like tell me what you see, right? So as we were looking at some kind of spectra or molecules, right? So that was another kind of chemistry related course. So yeah, and then you like have here something, right? Tell me what you see, right? So that tell yourself, your like friend or peer, what you see, and then toss those like details around or ideas. So then let's take a look at next things. It's going to be the ketone, right? I'm going to show some random ketone, which will be looking like this, for example. And all of a sudden, what if I have like a phenyl here, right? So phenyl here. So we'll assume that we are going to have only the reduction of the keto group, which is going to be the carbonyl, right? Specifically, a piece of the keto group will be reduced, right? So we're going to add H2, that's our reagent, on platinum as well as a catalyst. So then we're going to show the product. So this goes here, and that's our carbon. So for our intents and purposes, we did not consider the reactions of the phenyl group, and then we just assume that it doesn't react unless otherwise noted, right? So, but for now, just leave it alone. So even though there are double bonds that can be reduced, but the conditions will be like drastically different, right? So it's not going to be like that simple, right? So you have to use some kind of different conditions, basically. So for now, we'll just assume that we are reducing the ketone, right? So that's going to be our job to do that, right? So again, we're going to form the famous CH bond. Then we're going to form the OH bond, and that's it, right? So now we obtained our sp3 hybridized carbon, 4 single bonds. This carbon used to be also like having 4 bonds, 1, 2, 3, 4, all set, right? So things like that, so like are good to keep in mind. So, and yeah, so here we're going to make the alcohol. If you look at this, we're going to have the attachment of 2 carbons to the alcoholic carbon, right? So 1, 2, that's going to be a secondary alcohol, right? So ketones form secondary alcohol upon oxidation, and the, what's it called? Aldehydes form primary alcohols upon oxidation, right? So then we are going to move on to the next stage. So what do we have here on the next stage? It's going to be, I would say, further oxidation, right? So basically, we stop our reactions of ketones, or so we can think about the synthesis, right? So how do we make those things, right? So how to make, for example, like aldehydes, right? So for ketones, we will not be kind of like touching the synthesis of ketones. However, you can think about that as well, right? So they come basically from oxidation. So if you have the, so we do touch the synthesis of ketones, sorry. So we have some kind of like alcohol. Let's say it's going to be isopropanol, right? You can do any other secondary alcohol that you wish, right? With maybe like 16 carbons, 5 carbons, whatever, right? So you'll be able to generate it with your like imagination at least, right? So here I'm going to do the oxidation, right? So I'll just typically show the oxidizing reagent. And then as a result of this, you are going to remove H from here, from OH, and then H from the CH will be also lost. So as a result, you are going to have your ketone, right? So what about next aldehydes, right? So they are made from not secondary alcohols, but from primary alcohols. So let's show some primary alcohol like this one, right? So CH2. OH, right? So that's your primary alcohol. So here you have 2 kinds of reagents. You can have the mild oxidizing reagent, mild O in brackets, right? So, and then as a result, you are going to make the aldehydes. So let's show that. So 1, 2 carbon, and the 3rd carbon will be aldehydes. So just kind of basically this one loses H, and carbon loses also one of the H's, right? As a result, you are going to leave 1 H on the carbon, and now you are going to have oxygen without H. Minus H, minus H. OH turns into O, CH2 turns into CH. Then don't forget the double bond, which is going to be like one of the like features, must-have features of an aldehyde, right? So as a functional group. So then you can further oxidize your aldehyde, right? So maybe it's going to be like strong, right? So you can add a strong oxidation reagent just to make sure that you like, do the reaction, right? And then what's going to happen is that if you like see some kind of oxidation of aldehydes, so for now, so we'll just say it's going to be giving us the carboxylic acid. So here is a trick how to do that. So carboxylic acid, if you know, if you remember this group, so then you can like easily generate it from here. So leave this alone. This ethyl, right, stays, right? So COH will change into CO. This part will stay, and then instead of H, you are just going to have OH. And now you have your carboxylic acid functional group circled, right? So pretty good. So now let's take a look at what we have next, right? So previously, so we need to jump back to alcohols a little bit and look at the formation of ethers. That was our condensation reaction, so to speak, right? So let's quickly review that, right? So like basically for ether formation, so we need to consider alcohols as starting materials, reactants, substrate, whatever, right? The starting stuff that's on the left side of the reaction, right? So this is our reaction arrow. And then let's say we're going to have 2 identical alcohols. That's case 1, right? Let's say we're going to have isopropanol molecule, right? And it reacts with another isopropanol molecule. So it will form an ether. So what's going to happen is that you are going to technically remove H and OH, right? So water will be released. So you can also show it as a side product. It's not necessary, right? So then we can show it even under the arrow, or we can show it plus H2O on the right side, right? So that's fine. So now we're going to connect the parts which survive, right? It's going to be this O, and then here you are going to break this bond, and that bond is broken, right? So now you're going to connect electron and electron. So you're going to make a CO bond, right? Electron here, then this central carbon will also possess an electron. And now you're going to make a bond like that. So that's your ether. So COC, nice and easy, right? So another case, we can have like two different alcohols, right? Can be the case as well. So let's do something like that. The famous isopropanol, and then let's imagine it's going to react with a phenyl, with a phenol, with the phenol molecule. It's not going to be a problem either. So we'll remove the OH, and then this guy will have to lose H. Or maybe it will lose OH, then this guy will have to lose H, right? So either way, you will get water. So you'll have to get water, H2O, right? So then we have the free electron, and we'll have the free electron. So connect carbon, oxygen, make your product. So we are going to show the conditions. I didn't show the conditions last time, but it's going to be in the presence of H2SO4, and the temperature will be about 140 degrees Celsius, right? A little bit lower than the dehydration process. So as a result, we are going to have the following: carbon, oxygen. So we are going to form the bond, show two electrons, connect them, or make the connection. You don't have to show the electrons, right? So that's not necessary. So then they are implied, because if you know what you're doing, if you know what's going on, then you are in a good shape. So that's your like non-symmetric ether that you are going to form. All right. So then what else? So next will be, so we're going to take a look at the like future reactions, so such as the reaction of the thiols, right? So please review that. So for thiols, so it's going to be a real brief. So like number one, it's going to be the oxidation. We have some kind of like random thiol, right? So then what's going to happen is that typically in the oxidation, two molecules will have to be combined. So oxidation reaction takes place. And then as a result, we are going to have the following product, right? So it's going to be made from RS part. Then you flip the RS part and show it here on the other side. And then you make the SS bond. So sulfur is divalent. That's your oxidation, right? So then next one will be also two molecules of some thiol will have to be required. And then it can react with a heavy metal of some sort. Maybe it's going to be, let's say, Pb2 plus, right? So it's divalent, basically. So that's a clue for you, or key, right? So what's going to happen is that the following reaction will take place, right? So you need to break the SH bond again. Put the Pb in the middle, because it forms like two arms or two bonds, right? So from it, and then show the other SR piece. So I can flip it again, right? So here it is. Sulfur divalent makes two bonds, right? So then plumbum here, or lead in English, right? So it will make like one bond and another bond as well. So that's as far as the reaction go. I cannot physically review everything, so like don't criticize me here. So I'm doing my best, or I'm doing like, this is not even mandatory actually, but I'm doing it. Anyway, so next one will be, what's it called? That's going to be another, it's a little bit random, so, but we're going to take a look at the dehydration of alcohols and the Zaitsev's rule all in one reaction. Let's just do that. So sometimes you'll have like relatively complicated alcohols, such as this one. Let's say this is going to be your complicated alcohol, right? Here. All right, so, and now you're going to dehydrate it, right? So what are the signs of dehydration? You're going to use H2SO4 and relatively high temperature, higher than the ether formation, 180 degrees Celsius. So dehydration, let's remember how this happens, right? So you're going to identify the carbon, which is alcoholic, right? With the OH group directly attached to that. And then you're going to identify a couple adjacent carbons. So this one, and here happens to be another adjacent carbon, right? So both of them have an H, right? So which can be part of the water, which will be like part of the dehydration process, right? So now you can have potentially two molecules that can be formed, right? So let's say pathway 1, pathway 2. Conditions are the same, H2SO4 at 180 degrees Celsius. Okay, that's what we're going to have here, right? So let's take a look at this case, right? Condition, let's call it like number 1. This is number 2 on the top, right? So number 1. So let's imagine that this H and the OH will be dehydrated. So H2O is gone, right? And then you're going to make one compound, which is going to be looking like that. So you're going to make an alkene, right, as we remember, and then everything else will stay the same. Pathway number 2, let's say this OH and that H will be gone. So this H stays intact. Double bond. So now you have a different isomer, right? So this molecule is different from that one, right? So because of the like arrangement of the double bonds, right, throughout the molecule, for example, you can see the difference. It's not the same, right? So not the same two molecules. So what do we do next? Next, we are going to identify the carbons, right? So from the sp2 bond, I mean sp2 carbons from the double bond. Okay, they're here, right? So they are, let's say, in black. So these are sp2 carbons that are formed. It's going to be probably a good practice for you to show the expanded structures of those compounds, just to count the H's, right? Keep track of things. So, and then we're going to count the carbons which are directly attached to the entirety of the sp2 carbons. So this carbon here has no carbons attached to that, only H's. This carbon here has one carbon directly attached to that with one bond away, one bond distance, right? These are too far. 1, 2, because there are 2 bonds away, right? So that's what we consider too far. So direct attachment, it is just literally one bond, right? So if we look at this isomer, we are going to count more carbons, right? sp2 carbon number 1 has one carbon attached to that and one H. sp2 carbon number 2 has direct attachment to 1 and 2 carbons, right? So here we have one carbon total attached to the sp2 couple of carbons. In this case, in the top case, scenario 2, we'll have 1, 2, 3, 3 carbons total attached to those sp2 carbons, right? So now here we are going to apply the Zaitsev's rule and say which isomer will be prevalent, which one will be the major product. Well, turns out that according to the Zaitsev's rule, the compound, the alkene, which is more substituted, which has more carbons attached to its sp2 carbons in the double bond, will win, right? So this is going to be the major product, because again, this alkene has more carbons attached to its sp2 carbons of the double bond. This carbon is going to be the minor product because it has, according to the rule, right, less carbons attached to its sp2 hybridized carbons, 1 versus 3, right? So more carbons attached to the carbon-carbon double bond, like overall, is going to be the major product according to the Zaitsev's rule. This is going to be the minor product. All right, so then we are going to get to the, I guess, tail end of the, what's it called? Further reactions of aldehydes, right? So we considered like in our cycle of knowledge, so to speak, the quite complex reaction, but actually it's not too bad, of aldehydes, right? So which was called the formation of hemiacetal. That's going to be our last point, I guess, for today. So because like lots of people were like, so to speak, confused, right, or having difficulties with that. But if you practice, so which is what like you need to do, right, so you'll be having easier time with that, right? So now let's take a look at this hemiacetal and then acetal formation. So hemiacetal, so that's going to be our like step 1 in this kind of like complicated organic versus organic reaction, right? What do I mean by this? So we can have some kind of like aldehyde, let's say R, in the interest of time, could be some kind of alkyl chain. And then you literally just need to be able to redraw that and then leave it alone, right, on the left and right side. So then you'll have your aldehyde, which is going to be looking like that. And then let's imagine it reacts specifically with just one molecule of some random alcohol. Let's call it like that, right? So R prime could be some alkyl group maybe, right? With 6 carbons, 4 carbons, 69 carbons, right? Whatever it might be, right? So maybe it's going to be like 100 carbons, right? So possibilities are rife. So then we are going to have to form the new bonds, right? Which is going to be like that. We are going to have to make the OH bond in our new molecule of the hemiacetal. And we are going to make also another bond, which is going to be the carbon-oxygen bond, like this. Okay, so let's show what happens, right? So this reaction is reversible. It takes place in acidic conditions, and then we are going to make the following, right? So R just stays intact, right? Whatever it might be. So just kind of like leave it alone, right? So then I'm going to redraw this carbon, right? So with an H bond intact, CH bond stays intact. So then I'm going to position the alcohol carbon. R prime will be redrawn, right? So I'm going to make the carbonyl carbon and oxygen from the alcohol. They will be bonded. Okay, that's a new bond that I form, right? So then I'm going to not forget about this oxygen here. So what happens? That bond has to be broken. So the sigma bond survives. The pi bond is broken. So it's now hanging on one bond. Now we need to make a new bond, right? Between O and H. Just add H here. And here you go. This is your acetal. Divalent carbon, tetravalent carbon, divalent oxygen, sorry, divalent oxygen, right? So all kind of makes sense. It's not like somebody has 3 bonds instead of 4 or 1 bond instead of 2, right? Hanging in the air. So that's kind of like bad. So now you have the hemiacetal. Let's remember, let's imagine that we are going to take this now, right? So like, and then this is going to be now our reactant for the next stage, right? Which is going to be addition of the another molecule of some, maybe other alcohol, right? Who knows? We're going to add another alcoholic molecule here, let's say, right? So maybe it's going to be called, let's call it like OH, and then R with a double prime, right? So it's going to be also happening in acidic conditions, right? Reversible process. So that's your conditions. H plus, the sign of the acid, right? The proton, right? Which acid donated to the like reaction mixture, right? So now turns out here we're going to do some elimination, right? We're going to remove the OH and we're going to remove H, right? And then we're going to make a new bond, which is going to be signified with the green electrons. This electron and that electron on the oxygen will come together, right? So it's going to be CO bond will be formed as a result. So let's show the product. So what does it look like? So it's going to be looking like that. So that's going to be the right side, let's imagine, and then I'll just continue here on the bottom of the page. So R, C, H, O, R prime, redraw, right? So if you do it like 10 times, it will be like better, right? So then we have the electron. And then, so this is just like, forget about that. It's going to be eliminated. This will be eliminated, right? In the product that will be formed, right? So there's going to be no HOH. So then you're going to have OR double prime, OR double prime with its electron as well, right? So now you're going to make the CO bond because coincidentally, covalent bonds are made of 2 electrons, right? 1 electron is provided by each atom. So, and here you have it, right? So you have your carbon with 4 bonds, oxygen with 2 bonds, and that's it. That's actually like even like a little bit easier, right? So you only make 1 bond when you form now the molecule of the what? So this guy is called acetal, right? So that's a molecule of the acetal that is formed as a result of this reaction. So I hope it's been pretty comprehensive. If I forgot something, I forgot something. So, but again, physically, not everything can be squeezed into this review, but hopefully it was conceptual and useful. So, and that being said, I'm over time and bye everyone. We'll see you when we see you.